Now let's look at the third section of Chapter 4, Moment Generating Functions. Although the moments of most distributions can be determined directly by evaluating the integral or the sum, an alternative procedure sometimes make your calculation very simple. The technique that we used for that is called the moment generating function. The moment generating function, or the notation MGF, for a random variable x when it exists is given by the notation mxt, which is the expected value of e to the power tx. When x is discrete, this can be calculated as the sum of e to the tx times the PMF. This is the usual definition of the expectation. The summation have to be taken over all possible values of x. When x is continuous, the expected value of e to the tx, or the moment generating function, can be found by integrating e to the tx times fx dx over the support of x. The independent variable t here is usually the value that we are interested in, and t is in the neighborhood of 0. We need the knowledge about Taylor series and Maclaurin series in order to find or derive the moment generating function. Recall that the Taylor series expansion of a function fx is given by this expression. And this summation can be written as the sum of n goes from 0 up to infinity, f to the power n, which is the nth derivative of f evaluated at a, divided by n factorial times x minus a to power n. When a is 0, the Taylor series becomes the Maclaurin series. Then, instead of a, we replace a with 0. You end up with the Maclaurin series of fx, which is the sum of n going from 0 to infinity, the nth derivative of f evaluated at 0 now, divided by n factorial times x to the power n. Because a is 0, you have just x to the power n. Now let's try to find the Maclaurin series of the function e to the tx. Okay. Our function fx is now e to the tx. Okay. The first expression we have is f evaluated at 0. Okay, so if you substitute x with 0, you get e to the power t times 0, which is e to the 0, which is 1. Next, we need the first derivative of f evaluate at 0. So let's find the first derivative of x. So we get the derivative with respect to x. So t is like a constant. So if you do that, you get e to the tx. And the chain rule, the derivative of tx is t. So you have t times e to the tx. If you evaluate this as 0, when x is 0, you have e to the 0 is 1. So 1 times t is simply t. Then we need the second derivative of fx. Okay, so t is a constant. So if you do the second derivative, you again get e to the tx times t, and when you multiply that t by the t you got from the first derivative, you end up with t square. Then the second derivative of f evaluated at 0 is e to the 0 is 1. So this is simply t square. You can see the pattern. So if you continue this, say for the third derivative evaluated at 0, it will be t to the power 3. And likewise, if you go for the rth one, this will be t to the power r. Now let's substitute these values into our Maclaurin series. F to the 0 is 1. the first derivative of f evaluated at 0 is t. So you have t here and x over 1 factorial, which is 1. So you can omit writing it. So the second term becomes tx. Next term, the second derivative of f at 0, we found it is t square. So you have t square here times x square divided by 2 factorial. Okay, so here's the third term, t square x square divided by 2 factorial. Next, we need the third derivative with respect to 0. Okay, we found that it is t to the power 3. So you have t to the power 3 here times x to the 3 divided by 3 factorial. So here's the third term. Okay, so if you do the rth one, okay, you end up with t to the power r x to the power r divided by r factorial. Okay, so here's the Maclaurin series of e to the power tx. Okay. Now let's use this information in our mxt. mxt is expectation of e to the tx. When x is discrete, you can write that as the sum of e to the tx times px. Now we know e to the tx is this Maclaurin series. Okay. We'll use up to the rth one times px. Okay, now we are going to expand this one. Okay, so instead of px, I have used fx. We'll leave it like that. Okay, so our fx is actually the PMF. Okay, if you expand this term, you have px times 1, okay, or fx times 1. Then you have tx times fx, sum of t square x square over 2 factorial times fx, and so on. So we expand the series and then distribute the summation over all possible values of x. Since the summation is with respect to x, you can take t outside the summation and also the constant. Okay. So for the first one, we have the sum of x fx. Then the next one, the constant t outside, sum of x fx. The next one, t square divided by 2 factorial is the constant. You take it outside the summation, you end up with x square fx, and so on. Okay. And if you look at the summation here, the first one, if you take the sum over your PMF for all possible x, you know, this is the total probability 1. Okay, so that is the total probability 1. And if you can remember, in a previous corollary, we found that 1 is mu naught prime. That is the 0th moment, or when r is 0, the moment above the origin, m0 prime, which is 1. So we replace 1 with mu naught prime. Then the next one, you can see that the sum of x fx, this is the expectation of x. Okay, so you have ex, or that is the first moment above the origin. Okay, that is the notation. So we replace this summation by mu1 prime. In the similar manner, you do that same substitution for the sum of x square fx, x to the 3fx, x to the r fx. Okay, so that becomes the second moment about the origin, third moment about the origin, all the way up to the rth moment about the origin, and it goes so on, because this is the infinite series. Now what do you see in this final expression? So we can write mxt as mu naught prime is 1 plus t times mu. Okay, we know that mu1 prime is simply the mean of the x, random variable x, so it is mu. Then you have t square over 2 factorial, the second moment about the origin, third moment about the origin, and so on. So if you look very carefully at this expression, we see that uh, the coefficient of the expression t to the r over r factorial is always the rth moment about the origin, right? So the coefficient of t to the r over r prime is the rth moment about the origin. Okay, so if r is 1, t over 1 factorial is the first moment about the origin. When r is 3, t to the power 3 over 3 factorial is the third moment about the origin. So which means with the mxt you can easily find the moments, the first moment, the second, third, up to any rth moment about the origin. That will be the coefficient you get for the expression t to the power r over r factorial. If you want to prove this for the continuous case, we replace the summation by integration and you can easily prove this one. Now let's see how we can use this theory to find the moments about the origin using the moment generating function. The idea is to express our moment generating function in a Maclaurin series with these terms t to the power r over r factorial, and whatever you see in front of this expression, which is called the coefficient, that will be the moments about the origin. Okay, if you look at this simple example, our fx is e to the negative x and 0 otherwise. So let's start with the definition of the moment generating function. We know that mxt is the support of x is from 0 up to infinity e to the tx fx dx. Our fx is now e to the negative x. So this becomes 0 up to infinity e to the tx times e to the negative x dx. We can rewrite this as e to the negative x 1 minus t dx. Okay, so if you solve this integration, we end up with the antiderivative is e to the negative x 1 minus t. We get negative 1 minus t at the bottom. Evaluate this from 0 to infinity. We'll take the negative 1 minus t outside, constant. If you evaluate to the negative x 1 minus t from 0 to infinity, when x is infinity, you have actually negative e to the power negative x means e to the 1 over x times 1 minus t, right? When you have the negative power, which is the 1 over x to the 1 minus t. When x goes to infinity, you have 1 over infinity, which is 0. Okay, when x is 0, e to the 0 is, e to the power 0 is 1. Okay, so the negative and this negative 1, you'll end up with 1 over 1 minus t. So the moment generating function of the random variable x, when it contains the fx e to the negative x, the moment generating function is 1 over 1 minus t. Now this is a well-known expression where you can write the Maclaurin series, and you have to have t less than 1, otherwise you'll end up with undefined terms. Okay, because of this expression, we know for t values less than 1, the Maclaurin series is 1 plus t squared plus tr. If you want to check this one, you can follow the same method that we did here. Our fx is 1 over 1 minus t, and it is independent of x, so you can easily find the first derivatives, evaluate them in 0 and put it in this equation or the expression, and you can easily see that 1 over 1 minus t, the Maclaurin series, is 1 plus t square plus all the way up to infinity. Now remember, in our theorem, the moments, the rth moment or any moment about the origin will be the coefficient of the term tr over r factorial, right? Tr over r factorial. Although we see tr in our expression, we don't see r factorial. So we have to rearrange this expression. So we have t to the power r over r factorial in our expression. Okay. So therefore, what we need is plus 1 plus, when t is 1, we need 1 factorial at the bottom. If you insert a certain term which is not in the expression, okay, we have to cancel it out. Okay, if you divide, you multiply. So this is like you haven't done anything. Okay, now you have your t to the r over r factorial term for t. Let's do the same with t square. We need 2 factorial. Okay, r factorial. When r is 2, you need 2 factorial. If you divide by 2 factorial to cancel it out, you have to multiply it by 2 factorial. So this is like you haven't done anything to the t square, right? So you can do the same thing for all r values. Okay. You multiply and divide by r factorial. The whole idea is to get this expression in your Maclaurin series, because whatever you see in front of it, that becomes your r moment about the origin. Now you have the expression you want. Okay, so the coefficient of these terms, the coefficients of these terms, so here's the first coefficient. So that will be the first moment about the origin. This will be the second moment about the origin. This will be the third moment about the origin. This will be the rth moment about the origin. And this is simply 1 factorial, 2 factorial, 3 factorial, r factorial, which means for any moment about the origin, it will be r factorial. Okay, so the third moment about the origin is 3 factorial, fourth moment about the origin is 4 factorial, and so on. So this is how you find the moments using the moment generating function. So I'll explain the steps again. You get the fx, if it is a discrete case, the px. Then you use the definition of mxt and find the expression for your moment generating function mxt. Then expand it using the Maclaurin series. You know how to get it. Okay, here's the Maclaurin series. Using this expression, you find your Maclaurin series for whatever the moment generating function you get. Make sure to look at the properties of t or conditions you have to impose for t. After you find the Maclaurin series, try to get this expression t to the power r factorial. If you don't see it straight away, you have to rearrange the terms so you can get t to the power r factorial term in your Maclaurin series. Okay, after you do that, whatever the coefficient you get for this t to the power r over r factorial, those coefficients will be the moments of your random variable x. The main difficulty in this technique is that you have to find the Maclaurin series. Okay, you have to derive the first derivative, the second, third, and so on, and evaluate it at 0 and find the Maclaurin series. So sometimes it will be a little bit complicated. In such situations, you can use this theorem 4.6 to get the moments. If you need the rth moment about the origin, you can easily find it by taking the rth derivative with respect to t of your moment generating function and then set it equal to 0. Again, you take the moment generating function, find the rth derivative with respect to t, not with respect to x, with respect to t, and the answer you set t equal to 0, and that will give you the rth moment about the origin. Okay, so let's try an example and see how we can use this theorem 4.6. The random variable x has the PMF 1/8 3 combination x for the values of x 0, 1, 2 and 3. We have to find the MGF or the moment generating function of this random variable and then determine the first moment about the origin and the second moment about the origin. Now recall that 3 choose x or 3 combination x is written as 3 factorial 3 minus x factorial times x factorial. Okay, so let's start with the definition mxt. mxt is the expected value of e to the tx. This is the sum. X goes from 0 to 3. Okay, we have x from 0 to 3. E to the tx, px. Our px is 1/8 3 choose x. Okay, let's find the exact values when x is 0, 1, 2 and 3. When x is 0, we have e to the 0 1/8 3 factorial 3 minus 0 factorial times 0 factorial. Okay, so 3 choose x. I used this exact expression here. Now we move on to when x is 1. So this is when x is 0. Then we have x equals 1. We get e to the t x equals 1. So it is e to the t 1/8 3 factorial 3 minus 1 factorial 1 factorial. When x is 2, e to the 2t 1/8 3 factorial 3 minus 2 factorial times 2 factorial. And finally, when x is 3, we have e to the 3 times t over 8 3 factorial 3 minus 3 factorial times 3 factorial. So I don't have enough space here, so I'll write this in the next line. E to the 3t 1/8 3 factorial 3 minus 3 factorial times 3 factorial. Okay, so if we simplify this one, what do we get? E to the power 0 is 1. 3 factorial and 3 factorial at the bottom cancels out. 0 factorial is 1 by definition. So the first term is only 1 over 8. Okay, if you evaluate these factorials, you will find that it is 3 times e to the t over 8, 3 times e to the 2t over 8, 3 times e to the 3t over 8, which is 1 over 8, 1 plus e to the t to power 3. Okay, this is the expansion of the cube term. Okay, the sum of the cube of the sum of two terms. So if you do that, this is 1 plus e to the t whole thing to power 3. Okay, so here's our mxt. Now we have a nice simple expression. What we need is to get the rth derivative and set t equal to 0. So that will give you the rth moment about the origin. In this example, we need only the first moment and the second moment. Therefore, let's find the first derivative with respect to t and the second derivative with respect to t, and then try to find the moments. Okay, so by theorem 4.6, the first moment about the origin is the first derivative of mxt will wait at t equals 0. Okay, so here's our mxt. If you take the first derivative with respect to t, we get 3 over 8, 1 plus e to the t to the power 3, and then the chain rule, the derivative inside the function, we get simply e to the t. Now evaluate this at 0. E to the 0 is 1, and here we get 2. 2 to the power is 2, right? When you take the derivative, you have 3 and 3 minus 1, so 2. 2 to the power 2 is 4, so you have 3 times 4 over 8, which is 3 over 2. So the first moment about the origin, or actually this is the mean, or Ex, is 3 over 2. Now let's do the second moment about the origin. You need the second derivative of the mxt will wait at t equals 0. So here's our first derivative. You need to take the derivative of this term, and we are taking the derivative with respect to t, so this becomes the multiplication rule. So I have to take the derivative of the first one and then multiply by the second plus the second one times multiply by the derivative of the first one. So you have to include the multiplication rule. So that will be d over dt 3 over 8, 1 plus e to the t 2 times et. Then finally you evaluate at 0. So you'll find that this is, okay, so here's the first term, and the derivative of et is et, plus the second term is et, derivative of the next term is 2 times 1 plus e to the t and another e to the t. Then you have to evaluate this at 0. Okay, so if you do that, when t is 0, easily e to the 0 becomes 1. So the simplification becomes very easy, and you will find that this is simply 3. So this is the second moment about the origin, or Ex square. Okay, so if you know Ex and Ex square, which means you can find the variance also, right? You know the computational formula, so you can find the variance also. Sometimes the theorem, the 6, can be simplified or used very efficiently using the following information that we have in theorem 4.7. If a and b are constants, I'll rewrite the first one. It has some misprints. M of x plus a t is the expected value of e to the x plus a t. This is same as e to the a t times mx t. The second one, m of bxt, that is the multiplication of the random variable x by b. This is adding a constant to x. This is multiplying x by a constant. The expected value of e to the bxt is mx bt. And the moment generating function of x plus a over b t can be expressed in the third one. Okay, let's try to prove these three expressions. Start with the first one. So we have m of x plus a t. So if you use the definition, this is e to the x plus a times t px. I'm proving this for the discrete case, but if you want, you can replace the sum with integration, px with fx, and prove this for continuous case. So we split this one. We have e to the xt and then e to the at times px. E to the at is independent of x, so you can take it outside the summation. So we have e to the tx px. And you know, by definition, this is exactly the moment generating function of x, the definition of the mxt. So you have e to the at mxt. Okay, so that is what we want to prove. Okay, let's try the second one. Now multiplying x by a constant. Again, we write the definition. So you have e to the bxt now times px. So let's write this as e to the x times bt by combining b with t rather than x. Okay, so instead of t, now you have bt. Okay? So it is like another t, let's say t prime or something. So this is simply mx of bt. Right? Just rearranging the terms. Remember, t is a random variable, right? So you can multiply it by a constant. Then the last one, x plus a over bt which is e to the power x plus a over b times t px. By expanding, you can get e to the xt plus at over b px, and then splitting it, we get e to the xt over b times e to the at over b px. Again, you can take e to the at over b, it is independent of x, so it's outside the summation. You can write it sum of e to the xt over b px. Okay, so you have e to the at over b, and this is the moment generating function of t over b. Okay, so instead of t, you have a t over b here. Okay, so this is how you prove the theorem 4.7. And you can easily use these expressions when you have to simplify your moment generating function. In the next section, we are going to look at some inequalities, important two inequalities that will be useful in calculations, which involves the information on mean and the standard deviation or the variance. The first theorem, theorem 4.8, it's called the Chebyshev's theorem. If mu and sigma are the mean and the standard deviation of a random variable x, then for any positive constant k, the probability is at least 1 minus 1 over k square that x will take on a value within k standard deviations of the mean. So what all these lines are saying is the probability of x minus mu, the absolute value of x minus mu is less than k times sigma is greater than or equal to 1 minus 1 over k square. So when we say x will take on a value within k standard deviations of mean, okay, x will take a value within k standard deviations of the mean, that is k times the standard deviation within x minus mu. Okay, so I'll show you the graph, then you can easily understand what this says. Okay, so let's look at this expression, the absolute value of x minus mu less than k times sigma. What does this mean? If you want to drop the absolute value, how do you write this one? This is simply x minus mu within negative k times sigma and positive k times sigma. Right? So recall that if you use something like this, x less than 3, which means x is in between negative 3 and positive 3. So it's the same thing. So x minus mu is within negative k times sigma and positive k times sigma, which is, if you take this mu for the other side, so you'll end up with mu minus k sigma less than x less than mu plus k sigma. It's the same thing by taking mu to the left and to the right. Now we have an expression for x within these two values. Okay, let's draw the picture of the normal distribution, okay, for this expression. We have the mu somewhere here. You have mu plus k times sigma, so it will be a value somewhere over here. Mu plus k times sigma. So you add a value k times sigma to mu, so it will be somewhere here. You do the same by subtracting. So mean minus k times sigma. So it will be a value somewhere here. And you have the two tails. Okay. So this area is x less than mu minus k sigma. Right? So this line is your x, variable x. So this colored area or the left tail is all the values x less than mu minus k sigma. And this area, so let's say this is the area in the middle is area A, area B and area C. So area C is where x takes values greater than, see everything to the right, greater than mu plus k sigma. Okay. So which means you have in area B you have x minus mu less than negative k sigma. If you square this term, okay, when you square a negative value it becomes positive, so you end up with greater than or equal k sigma square. Okay, the sign changes because when you square a term, it becomes a positive value. In this side, what do you get? X minus mu greater than k times sigma. So no problem here, both are positive. So if you take the square term, still you have square of greater than or equal to k sigma square. Okay. Okay. Now let's start with the definition of the variance because it contains the standard deviation. Let's start with the variance. Sigma square is the expected value of x minus mu square. Okay, that we know. If you want to find this one for a continuous random variable, you integrate from negative infinity up to plus infinity or the support of x minus mu square fx dx. Our fx is now divided into three parts, a, b and c. So we write those three parts, three integrations, splitting this one integration into three. So we have b area, which is from negative infinity up to mu minus k sigma. So we have negative infinity up to mu minus k sigma x minus mu square fx excuse me dx. The next part is a, from mu minus k sigma to mu plus k sigma. X minus mu square fx dx. Next, the last part, from mu plus k sigma up to positive infinity x minus mu square fx dx. Now we have written negative infinity up to plus infinity of this function fx, splitting into three parts. Okay, so this is for b, this is for a, this is for c. Okay, we know for sure that the middle part contains all positive values. Fx is a PDF, so it is greater than 1. This is the square term, it is greater than 1, and you see the values within a positive area. So for sure we know for the integration in the part for the area A, this is non-negative. This cannot be negative. Okay. Therefore, we are going to drop this from our expression. Okay. So we know this is greater than 0. Therefore, we can write our sigma square is greater than or equal to the other two parts. If you drop this one, right? So your right hand side becomes smaller and the left hand side becomes bigger. So you have sigma square greater than or equal to negative infinity from mu minus k sigma x minus mu square fx dx plus, we have dropped this term, now only c mu plus k sigma up to plus infinity x minus mu square fx dx. Okay. Now what we found? We have found that x minus mu square is greater than k sigma square. Okay, so we can replace this with, because it is positive, greater than, so it tallies with our inequality. Negative infinity up to mu minus k sigma, we can replace x minus mu square with k square sigma square fx dx. We can do the same, right? For c also we found that x minus mu square is greater than k square sigma square. So let's replace that also. K square sigma square fx dx. Okay. Now we can take k square sigma square outside the integration because these are positive values. Sigma square, it's the variance, it is positive. Okay, when you square a certain constant, it becomes also positive. Right? So let's take k square sigma square outside, which will give you negative infinity up to mu minus k sigma fx dx plus mu plus k sigma plus infinity fx dx, provided that sigma square is positive and it is not equal to 0, you can cancel the sigma square. Okay, if sigma square becomes 0, you cannot do that, but it is provided in our theorem that sigma is not equal to 0. So you can cancel it in this inequality. So what do you get? You have k square in the left hand side. If you take it to the other hand, you get 1 over k square greater than or equal to negative infinity up to mu minus k sigma fx dx plus mu plus k sigma up to plus infinity fx dx. Okay, so this is actually the area B and C, right? And that is your whole fx minus a, right? Your whole fx minus a. So we can write this as, okay, so what is this area? Okay, this is our area B. If you integrate your PDF from negative infinity up to mu minus k sigma, which means that is the probability that x contains values less than mu minus k sigma. Okay, that is for the part B or area B. And then the right tail or part C, that is the probability x will have values greater than or equal to mu plus k sigma. Okay, so this integration means the probability, okay, when you have the PDF and integrating it. So this is the area under the curve actually. Okay, the area under the curve is the probability that the random variable x taking values greater than mu minus k sigma. C is the area under the curve, which is the probability that the random variable x taking values greater than mu plus k sigma. So you can write it like this. Okay, so these are the two tails, tail B and tail C. If you use the complement, okay, let's draw the picture again. Yes, A, B and C. So this probability is the probability x taking values in this area and this area. You know the total probability is 1. So we can write this as 1 minus probability that x taking values inside this mu minus k sigma. That is probability that x is within mu minus k sigma and mu plus k sigma. Okay, total probability is 1. Okay, so if this probability is the tails, the middle should be 1 minus, okay, that one. So what do we get? One minus probability negative k sigma x minus mu positive k sigma, right? If you take this to the other side, you get probability, and we can write this as x minus mu less than k times sigma greater than or equal 1 minus k over 1 over k sigma. So this is exactly the Chebyshev's inequality we have to prove. Okay, so take your time leisurely and study these steps one by one. Study this proof again and again and try to understand how we did the proof. Although the proof is long, using the Chebyshev's inequality is very simple. So if you want to find the probabilities for 2 sigma, 3 sigma and 4 sigma. Now remember these are inequalities. Okay. So the probability x minus mu absolute value is less than 2 sigma. Simply this is 1 minus 1 over k is now 2 to the power 2, which is 1 minus 1 over 4, 3 over 4, which is 75%. So the probability that the x is within 2 standard deviation of mean is 75%. If you need the probability, the mean is within 3 standard deviations. X is within 3 standard deviation within mean. So this is greater than or equal to 1 minus 1 over 3 square, which is 1 minus 1 over 9, which is 8 over 9. For sigma, now remember these are inequalities, not the exact percentage. It is the greater than. Okay, so it will be greater than 1 minus 1 over 16, which is 15 over 16, 93.75%. Okay. So remember, the probabilities given by just Chebyshev's theorem is only a lower bound, not the exact probability. This is the lower bound. Okay. So the probability that the random variable x is within 3 standard deviation of mean is greater than or equal to 88.89. Okay, or it can be 88.89% or more. Right. So this is the inequality. But if you know the exact distribution, you can find the exact probabilities. Okay, so for example, so this is our random variable x. The PDF is x over 2. The support is from 0 to 2. Find the probability that x minus mu is within or less than 2 sigma. You know, according to the Chebyshev's inequality, this is the lower bound for this is 75%. Right? That's the lower bound. But what is the exact probability? Okay, so if you need the exact probability, we have to find probability that x minus mu is within negative 2 sigma and positive 2 sigma, which is actually mu minus 2 sigma, mu plus 2 sigma. So which means we have to integrate fx. The lower limit is mu minus 2 sigma, upper limit is mu plus 2 sigma. So which means first we have to find what is mean and what is the standard deviation. Okay, so let's start with finding the mean. Mean is the expected value of x. The definition over the x of x dx. Support is from 0 to 2, x times x over 2 dx, 0 to 2, x square dx, you'll get x to the power 3 over 3, 0 to 2, evaluate 2 to the power 3 is 8 over 3, 0 it is 0. So you get the answer 4 over 3. So mean is 4 over 3. Next we need the variance. To find the variance, first we need the second moment about the origin, or ex square. So if you do that, you have x square, fx is x to the 2 dx. Take the antiderivative, evaluate it from 0 to 2. 2 to the power 4 is 16. So you get 16 over 8, which is 2. So which means the variance of x, or sigma square, is, remember the computational formula, ex square minus ex, all things squared, which is 2 minus 4 over 3, all things squared. If you do that, you'll find it is 2 over 9. But what we need is sigma, which is the positive square root of 2 over 9. Okay, which is 0.471. Now let's find the lower limit and the upper limit. Mu minus 2 sigma will be 4 over 3 minus 2 times sigma is 0.471. So you'll get 0.391. And then the upper limit, mu plus 2 sigma, is 4 over 3 plus 2 times 0.471, which is 2.375. Right. Now you have to be careful. The support of x is from 0 to 2. So the lower limit is okay, from 0.391 is within this interval, but 2.375 is outside. So when you do the integration, you do not do up to 2.375, because after 2, it is not defined, 0 otherwise, so you only integrate up to 2. Although mu plus 2 sigma is 2.375, our support of x stops at 2. So you have to use 2 here. Okay, otherwise your integration is wrong, because any value, if you evaluate this integration for any value greater than 2, the function is 0, right? So you have to stop at 2. Now let's find the exact probability. So this is the probability. X is in between 0.391 and 2.275. So you integrate from 0.391 up to 2. Okay, remember our argument. Our function fx is x over 2 dx. Okay. So that will be x square over 2. Evaluate from 0.39 up to 2. Square. So if you do this simplification, you'll get 0.9617. So this is the exact probability, and from the inequality we know that that should be greater than 75%, and yes, we have an answer which is greater than 75%. The final theorem for the chapter is the Markov's inequality. If x is a random variable with the mean mu, for which fx equals 0 for x less than 0, then for any positive constant a, probability x greater than or equal to a is less than or equal to mu over a. So what does that mean? So here's our distribution. Okay, x and px. So let's take a certain value a here. Okay, so the probability that x is greater than a is always less than or equal to the mean of this random variable divided by a. So that is the Markov's inequality. So if you look at the previous example, we found that, recall the previous example, we have fx equals x over 2 and we found that the mean is 3 over 4. Okay, so for any a, since the support is from 0 to 2, let's say our a is 0.5. Okay, the probability that x is greater than or equal to 0.5 is less than mean over a, which means it is less than 3 over 4 divided by a is 1 over 2. Okay, so this is only an upper bound that you get for a probability. Okay, so the Markov's inequality, it will give you the upper bound for a certain probability. If you want to find the exact probability that x is greater than 0.5, you can do that. Integrate your function and you can find the exact probability. I'll leave it as an exercise. Find this one and see whether you can get and value that satisfy this inequality. The value you get here should be a value greater than 3 over 4 over or less than 3 over 4 over 1 minus 2. Okay. So that is the end of chapter 4. We talked about the moments, the mean, the variance, and then the moment generating functions. And then we looked at two special inequalities, the Chebyshev's inequality and the Markov's inequality, which contains information on the mean and the standard deviation.